everyone. This is Rob Gray from ASU and the Perception Action Podcast. In this presentation, I want to talk about applying an ecological approach to basketball, looking at how it can be used for practice design and coaching. And I think this is relevant not only for those of people listening involved in basketball, but I also think it's really relevant to look at different sports and how they're using things like the constraints-led approach and variability of practice and porting across to different sports. I think that's a really useful practice to see what you can take from other sports and look what's been found in other sports. So hopefully you'll find this useful, even if you're not directly involved in basketball. So to start off with, I want to talk a little bit about this video that came onto social media a few months ago. For those that can't see it, this is Stephen Curry, arguably the best shooter in basketball over recent years, best three-point shooter for sure. Practicing by essentially repeating the exact same shot as much as possible over and over again. Right? He's shooting a corner jumper over and over again. Someone's feeding him a ball. And when this appeared online, there was kind of a flurry of activity from both different kind of views of skilled acquisition, arguing, this seems to support, the best player in the world's getting better through repetition, right? They're doing the same shot over and over again. While other people were arguing, no, that's not what it is. So I'm going to come back to this example in a second, but first I want to kind of use this as a springboard to contrast the two different approaches to skill acquisition. Right? So the two different theoretical approaches to skill acquisition. These really are, the way that I like to explain them is by looking at the relationship between different types of variability, right? So we can talk about variability in your performance outcomes, whether the ball went in the hoop or not. That's the endpoint variability, the variability of our performance. We can talk about the variability in movement that led up to that, right? Did you use the same elbow angle on every shot? Did you release it at the same height, in the same hand position, put the same spin on it? So on and so forth. So movement variability, and I'm going to break that down even further as we go. And then talk about, of course, from a coach's perspective, how does all that relate to variability of practice, what we're doing in practice? And the example of Stephen Curry seems to suggest, we need literally low variability in practice to get better at shooting. And so what are the two theories? We know the traditional approach, of course, is the idea that there's one ideal technique. There's one ideal way to shoot a three-point shot that we teach through repetition and correction. The coach, instructor prescribes the solution to you. Here's where you do with your arms. Here's where you release the ball. Here's where you put your hands. And they correct it when you deviate from it. So in this case, movement variability is noise, right? It's something that's taking you away from this ideal, right? So we want to correct it and get rid of it. So if we're going to come back to my variability of practice example, we want to get consistent outcomes, low variability in outcomes, which we want no matter what theory we're talking about. We want the ball to go in the hoop every time. This is achieved in traditional view through a repeatable shot technique. As much as possible, using the exact same movements to create the shot over and over again, right? And we achieve this going to practice, variable practice, through focusing on mechanics in practice, right? We're going to focus on your technique, what you're doing with your elbow, where your hands are, and we're going to practice through repetition. We're going to teach you the one correct way to do this. Okay, so that's the traditional view. Also, kind of built on this, so low outcome variability, which we want, is produced by low movement variability, which is developed through low practice variability, isolated shooting, repetition, and so on. From this, another important concept I like to talk about is the difference between adjustability and adaptability, right? In the traditional view, what we want to do is teach adjustability, right? So we're going to teach you this one correct ideal way to shoot, and you're going to develop presumably a motor program, this stored information in your head about the parameters for shooting, right? The structure of a jump shot. And then what you're going to do is learn to adjust that ideal based on the situation. So if you have to shoot from further out, or there's a defender in your head, a defender in your face, or you're on the move, what we're going to do in order to perform under these different conditions, which everyone acknowledges exists, where we're going to adjust our existing program, right? We're going to adapt it for these conditions. So we're getting repetition with repetition despite variation, right? So we're forcing our ideal to be able to reparameterize in our motor program to work under different conditions. Okay, so that's kind of a fundamental idea. So from that, we can understand how we should be using variability of practice if we follow this traditional approach, right? We should learn the fundamentals first, right? And I'm illustrating it here with baseball, but it applies to basketball as well. We want super low variability, isolated conditions, hitting off tees, dribbling around cones, shooting the same jump shot over and over with no defenders unopposed, because we want you to learn the correct technique, develop the motor program first. Then we're going to add variability later, right? We're going to add variability later to allow you to learn to adjust it. And importantly, the variability should be representative of some conditions we want you to adjust to, right? We're not going to add an oversized ball, right? What would that help? Why do you need to be able to adjust to a bigger ball? It never occurs in a game. So how we think about the theory shapes how we use variability in practice, right? Which everyone, I think, now understands is important in some way. So I think that's a key to why we need to understand theory, right? Why do people opposing this idea, and why has this been changing? And in my new book I have coming out, I call this a revolution in the way we think about this. Well, I think people like me and a lot of other people have identified a lot of problems with this. And I'm going to use soccer dribbling around cones as an example, but it also applies to passing drills in basketball or shooting the same shot over and over. The problem is we know we have very poor action fidelity, right? We're not using the same information that we would. And this doesn't always apply to basketball because in some cases you do have an open jump shot, but we're separating perception and action, right? In basketball, you dribble, in soccer, you dribble to get around an opponent. The opponent's position is based on information about the opponent. So we're coupling action. And a lot of these decompose. So another term we use is decomposing. We're taking a game and breaking it into skills, right, and into fundamentals, right? And this can be very boring. So I call this, this example of fake agility. Okay, so we're breaking it apart, and the assumption is we can put it back in right into the game. And the assumption is we can teach you a decomposed static jump shot, and you'll be able to put it into an actual game. That's the big assumption everybody's making. Okay. What is the alternative view? Well, to talk about that, let's revisit Stephen Curry's drill. A few weeks later, after he posted that video, he came out with there was an article in sports on ESPN that actually talked about what this was, and Stephen Curry pointed out this is not something he actually does in practice, right? He doesn't repeat the same shot over and over. As he says, um, Curry rarely takes more than a handful of shots from the same spot, right? Instead, he's mixing up different shot directions. He's doing wind sprints, so he gets fatigued between shots, things like that, right? So what he was doing in the video was actually just before a game, kind of a warm up. He called it a kinetic activation process, right? So it was not for developing skill, right? It was for something else. And so what he was doing, what you can see from this quote that I'm talking about, is he actually adds a lot of variability of practice. He's not just repeating the same thing over and over. And that on the surface is very consistent with the alternative view of skill, right? The alternative view of skill is, of course, there's not one ideal. This comes from the work of Bernstein through Gibson. The idea is that we can't achieve success by using the same movement over and over because the conditions are always changing. We need what Bernstein calls repetition without repetition, right? We need people to have their own solutions based on their own individual constraints, right? So there's not one ideal solution. We have to let people explore and find it. Movement variability is good because it allows for adaptation to different conditions. It's not noise that we want to get rid of, right? So we're not giving a solution. We're allowing the athlete to find it through guidance, right? We're not correcting. We're helping exploration, right? So that's the basic idea of the alternative view. If we go into my variability diagram, on the right, we still want consistent outcomes. Of course, like everybody wants the ball to go in the center of the hoop, right? That's no matter what theory you believe, that's what you want. But the idea in the alternative view is that we're not achieving this by repeatable technique. We're achieving it by repetition without repetition, repeating the outcome by not repeating the movement, by using slightly different body positions, slightly different joint angles, et cetera, and so on. And I'm going to talk about evidence for these from research in a little bit, right? So to get this repetition without repetition, we don't want low variability decomposed practice. Instead, we want to focus on adaptability in practice by using opposed shooting drills, shooting from distances, shooting on the move, doing what Stephen Curry did, getting fatigued between doing shooting drills and so on, right? So that's kind of the alternative view. And so we want, again, we want low outcome variability, just like in the traditional view, but this requires a significant amount of movement variability, okay, which is developed through a higher level of practice variability than we tend to use, right? This is the alternative view. So connecting this to the other example I gave, instead of focusing on adjustability, having this one ideal that we tweak and reparameterize for different conditions, we want to focus on adaptability, right? Learning to come up with a movement solution, right? So we're going to have almost an infinite number of solutions, right? Because the conditions are always changing, right? We would need instead of having repetition with repetition in the face of variation, we're doing repetition without repetition because of variation, right? We can't achieve the same outcome by using the same movement because the conditions are always changing, both internally, I get fatigued, I get injured, and externally, right? The defenders are playing me closer, I'm shooting from different distances, I have to shoot on the move, and so on. And again, this of course is relative, right? It's relative to the sport. And basketball is a really interesting one because it has a mix of both, right? For example, I always talk about running and playing football and running and sprinting. Obviously, one of those has much less variation and constraints than the other, right? Running and football has way more. Basketball has an interesting mix of some conditions where, like free throws, are always the same, pretty much, right? There's always some variations in the constraints, but then they have a lot of other things. So the idea of this alternative view is we want to encourage variability in practice. We do that by adding variability in practice conditions early on, right? We don't want to wait for you to develop the technique or the fundamentals, quote, quote, right? And then add variability so you can adjust. We want to add variability right away, right? So you learn to solve movement problems. And for this reason, it doesn't really matter that the variability is something that could occur in the game, right? Because we want to adding a weird size ball or having fewer number of players or doing different kind of things I'll show you in the research studies. Those things are fine because we're teaching you to adapt to changes and constraints, right? We're not teaching you specific adjustments to specific conditions, right? That's the big difference, right? That's a big difference in what we're doing. And the example, going back to my soccer example, what do we change from using cones? We change to we're playing soccer tag, right? Soccer tag is where you can either do the coach chasing the kid. You can do this in basketball as well for practicing dribbling, or you have kids while they're controlling the ball, they have to touch each other. Why is this good? Keeping your eyes up. Your main point, though, is your movements are coupled, right? You're coupled to information. I'm dribbling to the left because you're coming at me from the right, right? That's why I dribble. That's why I move from side to side, right? It has purposeful, functional action. It's not something just a skill I can separate out and then plug back in, okay? And obviously, it's much more fun for kids and engaging, right? So this is real functional agility. It's not fake agility. So I think one of the things I think we need to concentrate in basketball and a lot of other sports is moving away from these fake uh, things that we think we can plug back in, right? We need to keep them in context as much as possible and coupled as much as possible. So that's kind of the background, the two theories. Now I want to talk about some actual research on basketball. I mean, mostly it's not mine at all, but I've been involved, in consulting in some of these projects and things like that. Talking about whether it's consistent with this kind of alternative view. Remember, the alternative view, what we're going to talk about is movement variability required for good shooting, right? Do we want to be repeatable shot technique, or do we want to be adaptable shot technique where we can adapt to the constraints and things like that? What's the role of variability in practice and how to get there? I'm going to talk about as we go. So let's start by looking at the role of variability. Here's a very recent study that looked at muscle activation during free throws. Okay. And what they emphasize in their study is kind of what I've been talking about. Um, in basketball, most coaches would teach basketball shooting the idea you need a uniform, repeatable shot technique for free throws. You want to do the exact same movements as much as possible. Okay. Whereas, in the alternative view, we argue that no, having some variability, allowing from some variation, both within individuals from shot to shot and across individuals, can be useful. So what did they find in the study? So in this study, they used surface EMG, which is measuring the electrical activity from your muscles. Okay. And they wanted to see how it related to the success of the free throw. They took a team of basketball players, 3 different teams. They picked 5 players from each team. The teams were playing at different levels, right? So they're different skill levels. And they asked them to do 20 free throws. Okay. What did they find? Okay. What they found overall is not consistent with the idea that variability is noise, right? What they found was the highest variability in the muscle activation from trial to trial, okay, during the free throw was in the experts, right? Not in the novices, right? If variability is noise, if the key to successful free throw shooting is being able to a repeatable movement, right? The exact same movement every time, then what we should see is as you go up skill level, you should see variability go down, of course, right? If the key to being a good free throw shooter is being able to do the exact same movement every time, then we should not see this pattern at all, right? So it seems to be inconsistent. So the experts had 40%, the novices 36. Okay, so the highest variability in novice. Furthermore, when they compared inaccurate versus accurate shots, the variability was lower. People were more consistent when they were inaccurate, right? So again, not consistent. This is not consistent with at all. The idea that the key to successful free throw shooting is moving the same way every time. What your muscles are doing is varying from shot to shot, from execution to execution between performers, and the higher that is, right, obviously to a limit, the better, right? Not the worse, right? So this is really not consistent with the traditional variability is noise. We want to have you practice free throws under the decomposed exact same conditions every time, right? What we want to do is set, and this is foreshadowing what we're talking about practice design, right? We want to change what people are doing in the background, right? What people are standing around you, whether you're fatigued or not. We want to vary the conditions. When in practice do you do free throw practice, right? The start, the middle, the end. That's something we could vary as well, right? Because we want this variability, right? It's good. The research is supporting it. A few other studies, I won't go into all the details. This is a quote from this paper published in 2020 regarding the variability and performance relationship. Not all players achieve success when their throwing technique was close to the average, right? So this was by Coves et al. In International Journal of Performance Analysis in Sport. So basically what they found was that there was the traditional expert performance approach where you find the average technique used by a group of experts and you see how close you are to that. It didn't support that idea, right? People that were well aware from this ideal technique were doing quite good in free throws. Okay. Here's another study by Malloy and Ull in 2010. What they did was look at they did movement tracking kinematics for different shots when people missed and when they hit free throws. Okay, and this is Journal of Sports Science. What they found, right, another thing that we expect to see in the traditional approach, if we find, for example, if in the traditional approach, right, if we have the key to a free throw is a repeatable technique, right? Developing this motor program where I perfectly prescribe what my elbow is doing, my wrist is doing, where I release it. What we should expect, right, is that after I release the ball, my motor program, nothing should change, right? Because I pre-programmed everything, right? And what my elbow and shoulder doing should be the same on every trial because I'm doing a repeatable shot. This study, they looked at 15 college basketball players, and that is not what they found at all. This is showing the relationship between the wrist and elbow angle, okay, and kind of how the variability between them. And what they found is the classic, what we call in ecological approach in the perspective control, the funnel of variability. The variability between these two things is going down as you go through the shot, right? What this is evidence of, in the quote from the paper, the synergy or coupling relationship between the elbow and wrist angles to generate the appropriate ball speed is proposed as a mechanism determining the success of free throw shots in experienced players. So what's not happening is you're not using the same elbow movement and wrist angle on every shot, right? They're not pre-programmed. What's happening is they're varying together as a unit. They have a synergy between them. If your elbow angle is a bit too hot, opening too fast, your wrist angle goes a bit slower. That's what we call a motor synergy, a coupling relationship. It's not consistent at all with the idea that you have a pre-programmed repeatable shot technique. It's consistent with the idea that your shot technique is varying every single time by your joints compensating for each other. Okay, this kind of relationship. So that's another piece of evidence I think is consistent with this. Okay, so we have this idea again. We saw this. This idea seems to be that variability and movement variability is important. Have it consistent with repetition without repetition. Let's talk a little bit of research about how you get there, right? How do we get? So we saw this last slide I showed. We saw a great example of kind of the highest level in Bernstein's theory of learning, right? Reaching a motor synergy where my degrees of freedom and movement are working together. Let's look at some research that's looked at in basketball about how you get there, right? Talking about how you start out. And we're going to get into Bernstein's ideas of freezing and freeing degrees of freedom, right? So Bernstein's idea, of course, Bernstein introduced the degrees of freedom problem. The degrees of freedom problem basically is if I have all this choice in how to move, right? I could shoot a basketball shot just by using my wrist, right? The ball wouldn't get very far. I could use wrist and elbow by locking my shoulder. I could use wrist, elbow, shoulder, fingers. I could put my knees into it, right? So all those are degrees of freedom. They're the choice I have about how to move. And Bernstein identified the degrees of freedom problem, which is essentially, how do I know which ones to use, right? And he proposed that at the initial stage of learning, what we do is something called freezing, right? What we're going to do is take some of the degrees of freedom out of the equation by two different ways, actually. But one of the most basic ways, I'm going to lock one of my joints and not use it. So basically, it simplifies the movement problem because I don't have to know what to do with that joint anymore because I've taken it out of the equation. And let me illustrate this using volleyball, right? So imagine doing a volleyball serve, right? How do I do it? Look at it. If you picture in your mind someone doing a jump serve, right, where they throw the ball up really high and you jump up in the air and hit it, think of all the degrees of freedom involved in that, right? And lower body, upper body, wrist, angle, hand, that. How in the world as a novice would you know what to do? So one of the simplest ways you can solve this problem is by simplifying it using a much simpler solution, like doing an underhand serve. And the most simple underhand serve, of course, is just hitting the ball, keeping your elbow and wrist locked and just moving around your shoulder joint and hitting the ball over the net. And we can represent this kind of solution that you came up with in what's called state space. So we plot one joint against another. So if I plotted your shoulder angle, elbow angle on one graph, your elbow angle and wrist angle on another, where you fall in that space, right? The degrees of freedom problem is where do you go in that space? And where you fall is your movement solution. And this movement solution I just described is serving underhand by just rotating around your shoulder, right? Which, if you can see the video, you can see here. What this is essentially doing, right? We're doing all shoulder movement, okay? No elbow movement, no wrist movement. So in Bernstein's terms, what we've done is we've frozen degrees of freedom, right? We're locking our elbow. We're keeping our elbow arm straight, so we don't need to decide what to do with our elbow joint, when to bend it, when to rotate it. Same with the wrist. We're doing everything with the shoulder, right? And so we've achieved this solution. And this is what I call freezing type 1, where you lock one of the joints. The other type of freezing that you can get is where you have rigid coupling, so your elbow and wrist do the same thing, right? And freezing, this kind of solution is useful because it gives you some proficiency, right? You can start playing volleyball or basketball right away by using, for example, the underhand serve. If you couldn't get into a volleyball game until you learn how to effectively do a jump serve, not many people would be playing volleyball, right? You would get bored and you get frustrated, right? So giving you proficiency early, but it's not going to give you, in the long term, make you a very good volleyball player unless you develop this solution more. So let's look at some examples of people looking at how people do this kind of degrees of freedom problem. And this is a paper by Button et al. In 2003, looking at movement variability. They looked at 6 university students, and they measured a lot of motion tracking during free throws. So we're on to basketball now. We're away from volleyball onto basketball again. The sixth participant was a professional player, and they did motion tracking and video analysis to look at the ball movement and the ball flight. And the most interesting finding for me is they found good evidence of this freezing degrees of freedom. So what they did, I have here, and I can describe it. They have state spaces of the wrist and the elbow angle. What you can see is a lot of the kind of 4 lesser skilled players. If you look at the wrist angle, there's not a lot going on, right? So this is going throughout the movement. There's not much change in the wrist angle. So people doing free throws are mostly using elbow angle, very little kind of snap at the end in the wrist. That's freezing degrees of freedom, right? You're taking the wrist angle out of the equation. But as you get more skilled, you do what Bernstein called freeing degrees of freedom. So things that before were locked and rigid or taken out of the equation, now you add them back, right? Because it gives you more fine control, allows you to adjust to more conditions, and so on. And you can see that in these graphs. If for the now participants 5 and 6, they are getting much more kind of active in their shots, are getting much more variation, right? They're using, another way to think of it, they're using much more of the available solution space, right? Instead of just having a simple, using a combination of wrist and shoulder, and wrist and elbow. They didn't do this analysis, but you can kind of imagine, and you can sort of see it in there. There's some synergies going on. They're starting to work together as you become more and more skilled. So there is some evidence in basketball that seems to support this freezing to freeing progression as you learn to shoot. Okay. Another way that we looked at this, and this is a paper by Verhoeven and Carl Newell, published in 2016. Okay. They looked at 25 male college students from the University of Georgia. Again, they did motion tracking on this, and they had them do free throws with either their dominant or non-dominant arm. I'm just gonna focus on the dominant arm results. What they used in this was an interesting method. So I talked about movement variability in the alternative approach, right? We argue that movement variability is good, right? We want it. We want you to be inconsistent, right? We want you to vary in how you use your elbow from shot to shot. But of course, we don't want all variability is not going to be good, right? So what we need, I said we break down movement variability further. One way that we can do this is through what's used called uncontrolled manifold analysis, which always makes me think of getting my car repaired. But basically the idea, what we're going to do is separate movement variability into good and bad. Okay, and so how do we do that? Well, imagine a task where you're given a task, you have to push down on a surface with both hands where your combined force is 10 newtons. Imagine you're given a job of holding something down from blowing away, right? What we can do is create a state space where we plot your right hand force and your left hand force, right? So in this, now we have some degrees of freedom, right? We could solve this problem by having 5 newtons in each hand of force, equal force in the 2 hands. We could put all our force into our right hand of 10 newtons and let our left hand do nothing. Or we could do the opposite, or lots of other combinations of forces between our 2 hands. And the idea is that with this type of task, we can define what we'll call good variability. I like to call it potentially good variability because it's not necessarily good, right? But it's just moving along this line, moving from having equal force in both hands to having all the force in the left hand is potentially good because for example, you could use it to adapt to fatigue or injury, right? It's not just default on its own good. It just gives you room to adapt to constraints, changes in constraints. So we call this variability, UCM, variability along the manifold. It's potentially good. It's good because it's allowing you to adapt to constraints while still satisfying the performance criterion of producing 10 newtons total. The other type of variability going away from this is called orthogonal variability. It's bad variability, right? If I go from 5 newtons in each hand to 6 newtons in each hand, now I haven't achieved my performance goal, right? I've got, going back to my variability, the outcome variability is now getting high, which I don't want, right? I want it to be 10 total newtons all the time, 12. So moving in that direction is bad. So one fundamental prediction we have in this alternative view is that with practice and with training, we shouldn't see all variability go away in your movement, right? That's the old view, that we have to get rid of variability because it's noise. What we should see is a change, a restructuring of variability, so that we get more good variability and less bad variability. And what does this study by Newell show? What they found was there's kind of a trend. They didn't find super strong evidence as we find with other tasks. So this was, remember, free throw shooting. What's shown here, what they found was the ratio to good to bad variability increased as with people that were better performers, right? And they had a model where they tried to predict performance, free throw success. And what they found was that this ratio of good to bad variability was a significant predictor. Okay, so it does seem that restructuring this variability, allowing your shot to adjust from shot to shot, movement variability, but in the right way is important for performance. Maybe it's not as strong as evidence from other sports, and I'll talk about that at the end. Okay. So I think so that's one way we can break down movement variability, and there's good and bad variability. The other way that I like to do it is to break it down to, kind of using some of Bernstein's terms, into elemental and essential variables, right? So within movement variability, when we're talking about a jump shot, there are two kind of things I think we can separate, right? And let's look at this example in basketball, right? So I put all this on the screen here. So here's my variability diagram again. Over on the right, we have the performance outcome variability. We want that to be low. We want you to hit the center of the hoop every time. We want you to have the same shot trajectory every time, right? What I like to separate, and I think this growing body of research showing this, is essential variables and elemental variables, right? Because this is important, because it's not the case that we want all of our aspects of our movement to have a lot of variability in them, right? For example, in basketball, we might want an essential variable is the variable, how I define it, it's the variable that in your movement, the parameter you've decided you're trying to control using information, right? So maybe it's the release height. You're trying to move so that you release the height of the ball the same every time. Or it could be release angle. Both of those have shown to be really important for shot success, by the way, having consistent release shot, right? So to say that you have a lot of movement variability and you have repetition without repetition is not saying that you can't have some consistency in these essential parameters, right? So we might want to have the same release angle as much as possible on every shot. But underlying that, we have the elemental variables, which are what produces this. So the release height is produced by the movement of my joints, my elbow, shoulder, wrist, etc. So I can have a consistent release height by having variation in those joint movements, right? So I've been arguing that in most skills, we want some essential variables to have low variability. We want a consistent, in pitching and baseball, we want to have a consistent release point. In basketball shooting, we want to have a consistent release point, release height, release angle. But that's not achieved by having the same movements, right? The movements that underlie at the joint angles and the elemental variables are different. We get that through variability of practice. So here we have repeatability in movement. Do we want repeatability in movement for a skill? Yes, but in the particular variables, right? Not in the exact movement of the joints and things like that. Things like release height and release angle, these essential variables. Okay, so there's some of the background and the research I think is consistent. Let's look at how we actually get there, right? If we believe this approach, that variability, adaptability is good, how do we get there, right? So let's look at that. So first of all, I want to talk about one approach, the constraints-led approach. This is built on the model of Carl Newell, the constraints model, the idea that skill emerges from the interaction between the constraints on us, right? The constraints are in the individual ones, your own height, flexibility, etc. The environment, what the playing surface is like. If there's wind, we're playing outside basketball. And the one that's most important for coaches, the task constraints, the distance you're shooting from, whether there's an opponent in your face, and so on. and skill emergence from that. And so from this, we can look at how people develop a solution and how it relates to variability, how it relates to constraints. So the first one I want to talk about is one that I actually reviewed in a video a while ago, showing how people do vary their solution based on the task constraints, right? And this is just showing, looking at the released height, release angle, and the release speed. And what this study did was look at the relationship between those two and the shot success. And from that, you can again define what's called a manifold, right? There's a certain combinations you can think about in basketball of speed and angle you can release at it, right? If I'm going to, if a low speed and a low angle, I can shoot like a super low angle, low speed shot. Or if I want to shoot at a higher angle, which is actually better in basketball, I need to shoot at a higher speed. So there's these combinations of movements in the space that will work. And what this study showed, they look at college basketball players, they track their movements and so on. What they found was people tended to, everyone had their own kind of, there was 6 participants. Everyone had kind of their own solution space, their own manifold based on their own variability and consistently. But what they found was that most people that learn to shoot basketball move without any instruction at all, just based on the task constraints, learn to use the release angle that allows for the lowest possible speed. Okay, um, why? Because the amount of noise in the actual release parameters in the essential variables gets smaller, right? So this is a good example of adaptation to task constraints. So allowing people to adapt and adjust instead of telling them what exact angle you should shoot from and what speed you should use. You can see people do this to the task constraints. Okay. Show release, shooting at the lower release point also allows for more error, right? More variation, right? A lot in the actual essential variables that we were talking about. So I think this is showing an example again of task constraints in action. Okay. Another example, another body of research that we've seen growing in basketball is using the constraints-led approach. So in the constraints-led approach, what we're going to do as a coach is we're going to add some task constraint, usually, although you can use others, to try to push people towards using a different type of solution. Right. So we're not just adding random variation in conditions. We have identified we want to change about the existing solution. We add a constraint we're not telling people what we want them to do differently. We're adding a constraint to kind of push them and explore and try other ones. And we're going to give them feedback as well. And this, if you were interested in more in constraints-led approach, this is the page I've developed for collecting the research and describing it. But basketball, we've seen this. One of the common ways this has been used in basketball, some great research by Raul Odegens, is using visual occlusion training. Right, this is one of my favorite examples of using a constraints-led approach. So what we're doing here is we're going to systematically occlude part of your visual field. That's a constraint. We're adding a constraint. It's not random like using strobe glasses, like sometimes you see Stephen Curry using. We're going to add ones for a specific reason, right, to try to push you to a new solution. And let's look at an example of this. These are some in basketball. This, as I mentioned, was work by Raul Odegens. What they found they started by examining the task itself, which is always critical. Do a task analysis to understand before you try to manipulate. So they looked at shooters, and what they found was that some of the shooters were having a problem where they were actually releasing the ball while it was in front of their eyes, right? So they couldn't see the rim. It was impairing their shot performance, right? So we've identified a problem with the movement solution, right? We don't just change movement solutions because we don't like the way they look or they don't conform to some ideal. We've identified a specific problem with it, and they've shown this in their first research. What they did then was to take 6 shooters that had this flaw, and they used occlusion glasses. So these were glasses that could completely close and then be opened through an electronic switch. And what they did with these people was they had them shoot with the glasses closed to start, and they didn't open until their hand was past their eyes, right? So they couldn't see the rim at all. They had to learn to pick up the rim and look at it at the end of the shot. So essentially what they're doing is trying to change their movement solution, their gaze behavior, what information they're picking up at. And they compared it to a control group. And what they found, it was a very small sample, but they found some evidence of the improved shot performance for the group that did, from 31 to 39% success rate in shots. And this was they had both during a court test and in the game, right? So some evidence of this working. There's also, you can, if you follow the research, they have some stronger evidence for that idea. They've also done this using wheelchair basketball players. In this case, what they do is they have a screen essentially hanging from the roof of the gym, and you have to roll under it and shoot. What this does is, again, it blocks your view of the hoop for the early part of the movement, right? So what we're doing, the phrase I like to use, and this comes from Stuart Armstrong, is constraining to afford, right? We're adding a constraint, not being able to see the start or having this thing block your view, to encourage you to explore and pick up information closer to the end of their shot, which we know is good, right? And this study showed in basketball, it showed some clear effects. Um, there's higher shooting percentage with training, right? There's some limitations with this research. It was small samples and so on, but I think it's along the right path. This idea of constraining something to push people away. So they didn't tell people at all, you need to look at the rim, you need to release it later. They didn't give any prescriptive traditional instructions. They just added a constraint to practice. Another example of this is this study I talked about earlier in my podcast many years ago, actually, Tahiri et al. And this was in 2017, they did a study where they added an obstacle to in front of you that you had to shoot over, right? Again, research showing that having a higher release trajectory is actually better to a certain degree in shot. So what they did in the study, they had 24 participants that were split into 12 skilled and 12 novices. They basically compared two training conditions. They had in all conditions, people were shooting over the barrier. In one condition, the barrier was always the same. In the other condition, the barrier was changing in height from shot to shot. Okay. And the basic idea, if you think about it, the latter one on the surface, you would think would be better if we believe this alternative repetition without repetition view, because you're forced to being able to adapt to different launch angles rather than the same one. Okay. That's the basic idea. What did they find? They actually found no significant effects on between the two groups. The variable barrier didn't work better at all. In fact, for novices, it hurt their performance, right? And I think this is an important caveat at all this, alternative view and variability is good research. It needs to be appropriate for the level of the performer, right? We can't just throw a novice, really unskilled performer that hasn't established it's frozen the degrees of freedom, established the basic solution yet. We can't throw tons of variability at them. Essentially, it can lead to negative reverse effects. We need to kind of scale it up and do appropriate things. So this, again, is kind of counter evidence. As I said, basketball is not a perfectly clean in terms of support because of some of the differences from other sports, like the sport I study most, baseball. Okay. Here's a study published Landon in a college. This was published in 1993. So this is a really old one showing the variability of practice effect. Essentially, what is the effect of having people practice from the same distance over and over in blocks versus randomizing the distance of shots? So now we're not using the barrier. They found, not unlike the barrier study, they found an beneficial effect of varying shot distance, but interestingly, it went away. It was a short-term lived effect that went away when they tested people later, right? So I think basketball, there's a lot of evidence consistent with the ecological approach that variability is good, but I think some of the aspects of it, we need we needs to be relative to the variability of the actual game, as I mentioned before. Okay. Um, Here's another example of the constraints-led approach. This one, again, was using, this one used both so this is Rabalo and all. This is a recent one I reviewed on my YouTube channel. They used variability in visual ones. So they also included auditory. Interestingly, they blocked people's sound for controlling dribbling. They had 20 participants, novices and experts, and they looked at how adding these constraints changed the dribbling performance. Okay. And so then they compared it to a no occlusion condition. And what they found, they used a measure to assess variability called a Lyapunov exponent. Okay. They were looking at kind of how stable the movement is. What they found was that, again, experts, when you added these constraints, the way that they handle this is by increasing the variability. In particular, experts seem to show variability in the shoulder movements. Okay. Um, so experts were better at responding to these changes and constraints. They were better at adapting because they could use different movement solutions, have more movement variability. Okay, so that seemed to be a condition. So overall, to kind of conclude this whole thing, I think overall basketball is another sport consistent with this alternative view of skill. Skilled shooting in basketball requires repetition without repetition. The research seems to be supporting that. You use different muscle activity. You're using synergies between joints. You're repeating the essential variables as much as possible. So we're having low variability in release angle, release height, but not by repeating the same elemental variable, but not using the exact same joint movements every time, by using different ones, right? So we're using motor synergies, good variability, not motor programs and exactly repeatable delivery. I think the research is consistent with that, and that's of course the ecological review. More research is needed, I think, on some of these constraints manipulations and understanding how they influence and encourage good variability, things like visual constraints, doing things like the uncontrolled manifold analysis. So I think basketball is kind of right for understanding this. As I said, I think it's interesting sport because it kind of lies between, in some ways, between the continuum of total chaos of things like soccer versus very low changes in constraints, because you have things like free throw shooting that are very, very similar every time, and shooting an open jump shot can be very, very similar every time. So I think it gives this interesting combination of, to what degree movement variability is important and when to add it in practice. So, but at least for me, the initial research seems to support this idea that I was proposing. This, good outcome variability occurs through repetition without repetition, movement variability, adaptability, which we need to be encouraging in practice by using things like the constraints-led approach. So thank you very much for listening. I hope that you found that useful. You can find everything you want to ever know about me at perceptionaction.com. You can find about my podcast. You can help support the podcast by going to patreon.com/perceptionaction. So this is Rob Gray from ASU. Cheers for now, and keep them coupled.